The global smartphone landscape has been hit with what is arguably the most substantial and verified hardware leak in modern technological history. This is not a matter of speculative rendering, analyst supply chain guesswork, or sketchy social media rumors that frequently populate the internet months ahead of a standard consumer electronics release. Instead, the tech community has received a massive influx of direct engineering files, assembly blueprints, motherboard maps, prototype drop test photographs, and actual developmental evaluation videos regarding Apple's highly anticipated next-generation flagship smartphones, the iPhone 18 Pro and the iPhone 18 Pro Max. This unprecedented data exposure is the direct consequence of a sophisticated cyberattack targeted at Tata Technologies, one of Apple's primary manufacturing and logistics partners operating out of India. The security breach resulted in the unauthorized extraction of over 630 gigabytes of highly classified, internally restricted documentation outlining the precise physical and internal specifications of the upcoming devices. For a company as notoriously secretive as Apple, a leak of this magnitude, revealing structural schematics, component bills of materials, and empirical stress test records straight from the factory floor, is completely unprecedented and provides an unrestricted window into the future of mobile engineering. One of the most instantly striking visual revelations extracted from the leaked Tata Technologies data cache is a series of official engineering photographs depicting a live prototype of the device undergoing mechanical stress testing, specifically high-impact drop evaluations. These photographs have immediately settled a long-standing debate among enthusiasts regarding the primary aesthetic identity of the upcoming product generation. The device captured in the laboratory testing frames showcases an elegant, incredibly deep dark cherry coloration. While third-party accessory manufacturers and case mold fabricators have been circulating mock-ups featuring a somewhat washed-out, distinctly pinkish hue, the actual retail titanium finish revealed in these internal documents is vastly superior. It presents as an intensely rich, sophisticated true red that reacts dynamically to simulated ambient lighting conditions. Historical context from previous product cycles highlights this discrepancy perfectly. Looking back at early case dummies for older models compared to their final physical shelf versions, the raw production titanium consistently delivers a premium visual depth that plastic injection molds can never replicate. The leaked engineering images confirm that this refined dark cherry hue will serve as the signature cosmetic identity for the premium tier, establishing a stark visual contrast against older generations and pairing seamlessly with high-resolution user interface design elements. Beyond the introduction of the signature dark cherry finish, the leaked laboratory drop test videos also display the larger counterpart, the iPhone 18 Pro Max, rendered in a striking silver color variant. Close examination of these high-fidelity frames reveals three immediate, highly consequential evolutionary departures from legacy design conventions. The first major transformation involves a profound shift toward monochromatic design cohesion. On previous premium models, a distinct dual-tone visual profile was highly prominent, particularly on the silver variants where the rear frosted glass panel leaned heavily toward a clean white aesthetic while the surrounding polished metal perimeter structural band remained a bright metallic silver. The new engineering documentation shows that Apple has completely abandoned this two-tone approach. The rear glass substrate has been meticulously color-matched to the exact tonal register of the unibody structural frame, resulting in an exceptionally unified aesthetic that feels significantly more modern and visually integrated. The second major structural alteration identifiable in the leak material is a clear and intentional increase in overall chassis thickness. The physical geometry of the unibody frame is visibly deeper than its immediate predecessors, verifying early manufacturing rumors that the next-generation premium devices would embrace a denser, more substantial physical profile. Rather than continuing an aggressive, decades-long pursuit of extreme device thinness at the expense of internal volume, the engineering documentation indicates a deliberate prioritization of functional utility. This extra spatial volume within the chassis is explicitly allocated to house a radically larger internal battery and a more robust thermal dissipation system designed to handle prolonged high-performance computational workloads. While this adjustment means the device will possess a heavier, more brick-like presence in the hand, the trade-off is aimed squarely at power users who demand uncompromising battery longevity and sustained processing throughput. For consumers who prioritize an ultra-slim, lightweight form factor, the wider product strategy offers alternative options, but the premium tier is intentionally maximizing raw capability. The third external characteristic highlighted by the prototype video is an even more aggressive protrusion of the rear camera module housing. The independent lens elements extend noticeably further from the rear glass plane than seen on any previous generation, a design evolution that aligns perfectly with the comprehensive internal sensor upgrades detailed within the leaked bills of materials. This increased physical footprint is the direct spatial consequence of a monumental leap in optical engineering. According to the compromised supplier schematics, the premium lineup will officially transition to a highly advanced, custom-engineered primary image sensor designated as the Sony IMX905. To fully appreciate the scale of this hardware upgrade, it is helpful to trace the architectural lineage of recent mobile imaging sensors. The baseline consumer models have historically relied on iterative versions of the Sony IMX904 sensor, a reliable component that has traced its origins through multiple product lines. Meanwhile, the previous premium iterations utilized the Sony IMX903, and prior to that, generations relied on the IMX803 architecture, which retained consistent baseline specifications while slightly adjusting readout speeds to accommodate 4K video recording at 120 frames per second.